back. Our next guest is Dr. Peter Dsouza, who uses DEM simulations to do research in particle rheology. Hello Peter, please introduce yourself.
Hello, I am Peter. I'm a senior scientist at RCP, the Research Center for Pharmaceutical Engineering in Graz. I work on understanding the basic behavior of flowing powders when applied to pharmaceutical manufacturing processes. These are specifically oral solid dosage forms such as tablets or powders or any sort of powders in pills that you may need. I also do fundamental research in flow fields, so mixing of different fluids in injectables and parenteral delivery systems.
So why do you use the discrete element method for your research?
Powders, unlike fluids, are a little more complicated. So it's hard to figure out how any applied force on a bed of powders results in a flowing powder field. Fluids, you have something like viscosity to tell you how well a fluid flows. Until we've developed that relationship between applied force or stress on a powder field to the resulting flow field in the system, DM helps me build and design process systems used in the industry so that we have results now, and B, get the fundamental flow behavior of powders. Why do they flow the way they do? Because if you look at individual powders or individual particles as we do in DM, you scale it up to the full system, you get a sense of how the system behaves. And I think that's where DM plays a crucial role in my research.
And on which systems do you apply the method?
You can use DM simulations in a lot of different systems, but to do fundamental research, you want to keep the system as simple as possible. One of the simpler systems are viscometric flows. These are devices used in rheometers, where the stress that you apply to a system is perpendicular or orthogonal to the flow direction. One such example is the Taylor-Couette flow, where you have a pair of concentric cylinders, one rotating, the other stationary, and the flow in between. Another example is a split-bottom Couette cell, which is an extension of the Taylor-Couette cell. Remove the inner cylinder and have only the base of a rotating disc in the system. And this is the device that I applied DM to during the course of my research during my PhD days.
Okay, so the setup of the experiment is rather simple. It's just a cylindrical container where the center of the bottom is rotating. And because of the friction between the particles and the bottom, the particles are also in motion. Which flows can you detect in the particle field?
In viscometric devices, you have what is known as a primary flow, the expected flow of the test material in the direction that you apply motion to, of your boundary condition. What we found through DM is that in addition to this primary flow, there are these secondary vortices that are formed. Now, secondary flows are not unheard of in fluid dynamics. So, for example, in Taylor-Couette flows, you have Taylor-Couette vortices, which are consequences of this push-pull between centrifugal forces and inertial forces. For powders, we found the presence of secondary flows even at very low inertial numbers, and that is a really cool concept that DM helped us find.
I think it's quite easy to understand how the primary flow is induced. But what leads to the creation of a secondary flow?
Powders are funky because sometimes they are like fluids, sometimes they're not. In this particular case, the particular particles have a property known as dilatancy because powders, individual grains cannot be compressed beyond a point. If you want to shear material, these individual particles have to push each other out of the way. This creates this low density region in regions of shear, also known as dilatancy, a cool phenomena found by Reynolds of Reynolds number fame over 100 years ago. The presence of this dilatancy is what causes the secondary flows. So as particles push each other out of the way in regions of shear, you have other particles filling those voids in, those regions of low density. And then this continues further and further, and then you have more particles pushing each other out of the way, more particles coming back into the regions of low density. A very slow flow, but a flow that's visible on reasonably long time scales. It's like you see here.
So if I understand that correctly, the motion and the stresses between individual particles create a density difference within the particle field, which is called dilatancy. For what is this knowledge needed in research in the broader sense?
To some extent, in terms of application, these sort of flows can give you an idea of how well the powder mixes or demixes. In my research, I've only done this for a single component powder and I haven't tested this for multiple components, but it sort of gives you an idea in that general direction. But the way I have used this in my research is when you want to figure out the overall physics that affect the flow of powders, how does stress-strain relationships work, you have to ask yourself, how does density and density difference affect your flow? So then when you have a constitutive relationship, a relationship between applied stress and resulting flow behavior for a powder, you now know, because of the research done on dilation-driven flows, that there is an influence, and we account for this in the equations that we build in our system. This makes it easier to get more accurate systems when you're solving analytical equations for flow behavior, and you're able to capture additional phenomena that previous equations were not able to capture.
Peter, thank you for your introduction into your research. If anybody is interested, check out some of Peter's papers. They are added in the additional literature section. That's it for this video. Thanks for watching and see you next time.